This is problem 2-112. It's on page 105. Consider a classroom for 55 students and one instructor, each generating heat at a rate of 100 watts. I almost said 100 kilowatts. It would be a lot of heat. Lighting is provided by 18 fluorescent light bulbs, 40 watts each, and the ballasts consume an additional 10%. Determine the rate of internal heat generation in this classroom when it is fully occupied. All right, so let's sketch the classroom. Probably should make it a little larger than that. We draw all the people as if they were one, and we know there are 56 people, and each person gives off 100 watts. So basically, 56 times 100 means that heat generation by people, Q dots of P, would be 5,600 watts. Okay, the lighting is 18 fluorescent light bulbs. We've got 18, each at 40 watts, but the ballasts, which there's one ballast per bulb in this case apparently, is 10 watts. So really, those two things go together. Okay, make sure I got that right. No, I'm sorry, it's not 10 watts, it's an additional 10%. So basically what we have to do is multiply by 1.1. Okay, so there's our additional 10%. Now this is kind of interesting. Let's calculate the amount of heat output by the bulbs. So 18 times 40 times 1.1 is 792 watts. So there's the, let's see, let's do it this way. So this is Q dot, I hate to use L, we're going to use that later for something very important. So instead I'll just say FB for bulbs, not for Facebook, but for bulbs, for fluorescent bulbs. Now it's kind of interesting to note that the, it's supposed to be a 9. It's interesting to note that the people actually put off a lot more heat than the bulbs. And you might not think of people as putting off heat, but if you ever have a party in your home or in your apartment or a small space and you have a lot of people there, you'll notice pretty quickly that the room warms up very quickly. I experienced this one of the few times I went to a game when I was on the main campus. I went to a football game and watched Purdue get beaten by Notre Dame. And it was the first and only football game I went to while I was there my whole college career. And it was interesting because it was actually late fall, as I recall, and it was pretty cold outside. It was chilly. But as soon as I got into the stadium and sat down, and there were so many people around, even though it was an open air stadium, it was a lot warmer in that stadium. That's because each person's body was putting off energy, or you have chemical processes going on in your body, and there's waste heat that's given off from your body. This is something that animals will use too. Some animals will stay together closely during the wintertime to conserve heat. Works very well. So anyway, it's interesting to note these heat loads, and the question is, determine the rate of internal heat generation in this classroom when it's fully occupied. So basically, the internal heat generation is just what is generated by the fluorescent bulbs and what's generated by the people. So if we just add those two together, 5,600 plus 792, then this is 6,392 watts, or 6.392 kilowatts. Almost 6,500 watts. Now, why would you care about this? Well, the reason you would care is if you're designing the HVAC system for this room, you need to know at what rate the HVAC system needs to be able to extract energy from the room. This is not really a simple problem because an air conditioning system, which is what would serve this purpose, needs to be able to keep the room comfortable. Well, comfortable and temperature can be two different things because, at least in our area of the region here in southern Indiana, there's two things that air conditioning has to do. It has to reduce the temperature of the air, but it also has to pull water out of the air and dehumidify the air. So if you have a room sitting still with no heat load because nobody's in it, and yet you want to maintain the temperature of that room, you can do it, but it could potentially become more humid in that room. Where would the humidity come from since there are no people there? Well, it could be many places, but mainly just diffusion from the outdoors would be one place. And so the air conditioner simply wouldn't run as long because there are no people in the room. There's no heat load. But then, see, so it's a trade-off, and you might actually choose to have the air conditioner have multiple stages so that it can actually run longer at a lower capacity. Now, when it runs at a lower capacity, it's not like you're wasting energy. It requires less energy to run at lower capacity, and it can just run longer, and thereby not only cool the temperature of the air, but also extract water from the air. It's reduce the humidity.